Hi there everyone, and welcome back to week 14 of the Maths Tutor exam countdown. So as you can see from your title there, week 14 is all about trigonometry. And I have linked two very good videos for you in the chat. So the first one there is a long question from the 2015 exam paper, and it's the question on the golfer and the golf course. And the second one is the derivation of the sine rule, which is required for the Leaving Cert higher level course. Okay, so hopefully you find those of some use. And remember, there's loads of resources for you on the Maths Tutor website also. So let's jump straight in. We're going to have a look at hopefully two or three exam questions today, going through a multitude of things from the trigonometry course. You're going to see some proofs to start with, some 3D problems, and some problems involving sine and cosine rules. Okay, so we're going to start with a relatively recent question. This is coming from the 2019 paper 2, and it's question 4. So what we're asked to do is we're asked to show that cos 2 theta, so that's a double angle, is equal to 1 minus 2 times sine squared theta. Okay, so we'll just remind ourselves, I suppose if I zoom out here, we'll remind ourselves of our log tables, and in particular for this question, the log tables on page 14 and on page 13. Now, again, look, there are more than one way. There's more than one way of answering these proof questions normally. So I'm just going to show you one way. We're going to start with the left-hand side. So my aim is to start with the left-hand side and work as far as I can in order to try create the right-hand side, so using the identities. So I'm going to start with cos 2 theta, and I know that cos 2 theta is exactly the same thing as that's just cos of theta plus theta. Okay, so we have what we call a compound angle there. And if I go back to my log tables here, you will see right there at the top of page 14, we have a formula that tells us how to simplify or write cos A plus B in a different form. So I'm just going to take exactly that down into my question box here. So it's telling me that cos of A plus B is equal to the cos of A times the cos of B minus the sine of A times the sine of B. So if you like, in this question, my A is theta and my B is also theta. Okay, so I'm going to basically sub in here, but my A is theta and my B is theta. So what I end up getting is cos of theta times cos of theta minus sine of theta times sine of theta. So I'm using my compound angle formula to rewrite the left-hand side as that. Now, you will notice that cos theta times cos theta, well, that's just cos theta all squared, or as we write it in trigonometry, cos squared theta. Also, sine theta by sine theta, you're going to notice that that's sine squared theta, and there's obviously a minus in the middle. Okay, so next we're going to have a look at, so I suppose if you keep an eye on your formula or your answer up here, we have no sign of a cos squared theta. So our job next, using our identities, is to try change that cos squared theta to something that involves sine squared theta. And you should be very, very familiar with, from page 13 of your log tables, this identity, cos squared A plus sine squared A, comes up quite a bit in trig proofs and in trig identities. And what we can do is we can rearrange that to get it to cos squared A is the same thing as 1 minus sine squared A. So if you have the cos of an angle and you square it, that's exactly the same as taking the sine of the angle squared away from 1. So that is our identity, if you like, that changes from cos to sine or vice versa. So what I'm going to do back here is, instead of my cos squared A, I'm going to change that into 1 minus sine squared A, because that identity from page 13 of your log tables, sine squared theta, told us that we can do that. And obviously this is just coming down there also. So putting like terms together, we have a minus sine squared theta and a minus sine squared theta. That's giving me 1 minus 2 sine squared thetas. And that is exactly what we wanted to have up here on the right hand side. So like I said, start with the left hand side, work your way through using your identities, and with practice you'll get better at recognizing which identities we use in which question, and work your way across to get to the right hand side. Okay, and you're picking up marks all along the way anyway. Okay, so part B of that question was this famous cube question. So as you can see, looks quite tricky. First of all, it's a 3D problem, which a lot of people find quite tricky. And secondly, there's absolutely no numbers here, or no letters or anything. So you're really starting with a blank canvas. So if we look at what they're asking for in the question, first of all, you're asked to find the cosine, so that's your cos, of the acute angle between two diagonals of a cube. And you can see that's marked right there in your diagram. Okay, so I'm going to start by, it's a cube, so we know it's a cube, so we know that all of the sides are exactly the same. Okay, and before I mark in the sides, I'm going to name some corners, name some vertices of this cube, so that it's easier for me when I'm running through the questions so that everybody can follow me. So I'm going to call this corner up here A, this one down here B, C, D, and I'm going to call this point right up here E, and this point right down here F. So look, again, it doesn't make a difference what you call them once you use the same labeling notation throughout your question. And I'm also going to call this point here, where the two diagonals intersect, I'm going to call that point P. Okay, so now at least we are hopefully on the same page. And because it's a cube, all of the sides of the cube are going to be exactly the same. So that means that B to F, I'm going to call it X, because there's no numbers. I'm going to put in my own variables. F to D, I'm going to call that X as well. And then your height here, C to D, is going to be X also. Okay, so what we're going to do is we're going to start with the base of the cube. So we're going to start with the bottom of the cube, and we're going to try work our way up to this triangle here, because that's where the angle that we're looking for is. So first thing I'm going to do is I'm actually going to cut in half the base of that cube. And I'm going to draw out that triangle, BDF. I'm just going to draw it out for myself. I have loads of space here. So we've F, we have D, we have B, and as I've just marked, distance from B to F, I've called it X, and from D to F, I've called it X as well. And you might notice I've drawn that as a right angle triangle because it's a cube, so our angles at the corners are going to be right angle triangles, okay? So you might remember we had a flow chart, and in our flow chart, we asked ourselves, the first question we ask ourselves, is the triangle right angled? And if you answer yes to that question, well, there's always two things that you can use. You can either use Pythagoras or sine, cos and tan. Sine, cos and tan are probably only useful if you have an angle. Pythagoras is useful if you know two sides of the triangle and you're looking for the third. So in this case, we are essentially looking for this side here, which we have called BD. And we're going to use Pythagoras to find that side. So Pythagoras' theorem, h squared is equal to a squared plus b squared, or c squared equals a squared plus b squared, or h squared equals a squared plus o squared, whatever way you have learned it. So my hypotenuse is always the one that's directly opposite the right angle. In this case, that's BD. So that's going to be BD squared is equal to a squared, which is x, plus b squared, which is also x. So that's giving me BD all squared is equal to, well, these two are the same, so that gives me 2x squared. And to get rid of the squared, we're going to square root the left and the right hand side. So what we end up getting is BD is the square root of 2x squared. So to simplify that, well, the square root of 2 is just the square root of 2. And be very careful here, you're square rooting an x squared. So that just cancels each other out and we're left with x. But I'm just going to mark that there because the x is not underneath the square root anymore. because the square root and the square root just cancel each other out. So root 2x is the length of this side here. So I'm just going to mark that very briefly into my triangle, root 2x. Okay, I'm getting closer to that triangle that I want to get closer to. So I'm just going to mark over here on the diagram. The next triangle I'm going to look at is this one here. So the triangle BCD. And again, just to make life a little bit easier on myself, I'm going to draw out that triangle over here. So again, it's a right angle triangle at the point D. B is over here, C is up here, and we're going to mark in everything that we know. So we know that this side is X, just based on my diagram. And we've just worked out, remember, up here, that BD is root 2 with an X outside the root. Okay, and like I said, we're getting closer to this triangle in here. So this time, we're going to be able to work out what the length of BC is. Pythagoras' theorem again, because we know two sides of the triangle and we're looking for the third. So that's giving me, my hypotenuse here is BC, and one of my sides is x squared and the other one is root 2x all squared. So be very careful with that. Just put it into brackets and we'll work that out on the next line. So what we end up getting is BC squared on the left hand side equals x squared plus. Now be very careful here. What you have is you have a root 2 and you're squaring it. So that's going to give you 2. And you also have an x here and you're squaring it. So that's going to give you x squared. So what that gives me is BC, or the length of BC, is, well, we have an x squared and a 2x squared. That gives me a 3x squared. Sorry, that should be BC squared. Again, square root both sides, and the same as we had above, that's going to give me root 3 and the x on the outside. It's exactly the same as we had up here. Okay, so back to our diagram. It's a very good idea in trigonometry to fill in on your diagram as you go, just to make life a little bit easier. So this line all up here is root 3 times x. So as we know, the diagonals of a rectangle or the diagonals of a square, they always bisect each other. So basically, if that full line, a little bit hard to see on our diagram, but let's just get rid of all of that colour for you for a second. This full line up here, that is root 3x. So therefore, the distance from B, that should have been B, and that one should have been C, and that we said in the middle was the point P. So the distance from B to P is obviously half of this distance here. Okay, so the distance from B to P is going to be half of root 3 times x. Okay, and that can be written as root 3x over 2. Why? Well, because the diagonals bisect each other. So let's have a look at what we have. We're eventually, after all our work, we've gotten into this triangle ABP here. So I'm going to draw that triangle out. And I'm just going to move over here as I'm running out of a little bit of space. If that happens in the exam, obviously, you have extra paper at the back, or you can ask for some extra paper. So this is what we're looking for in here. Filling in what I know. Well, I've just found that BP is root 3 over 2x, and AP is going to be exactly the same on the other side, obviously. And we also know that this length here, so that's just the height of the, this length here, that is just the height of the cube. That's going to be x, as we said, so we're going to mark x in there. So as you can see, we know, well, we don't know them, but we have an expression in x, it's still a variable, for 3 sides of the triangle, and we're looking for a angle. So it's not a right angle triangle. Sine, cos and tan, Pythagoras are no use to us. We don't know a side, an opposite angle, and one other piece of information. So sine rule is no good to us. So straight away, we need to go to the cosine rule. So your cosine rule, a squared is equal to b squared plus c squared minus 2 times b times c times the cos of the angle A. And as we remember, the side that you start with needs to correspond to the angle that you end with. So they need to be opposite each other. So we're obviously going to start with the side x, since this is the angle that we're looking for here. So it becomes x squared is equal to, and it doesn't matter which one of these and which one is b and which one is c. So that's going to give me root 3 over 2x all squared plus root 3 over 2x, x all squared minus 2 times root 3 over 2x times root 3 over 2x times the cos of the angle A, which is what we're looking for. Okay, so as you can see, we are now left with an equation in one variable, which is always solvable. So simplifying, we're getting x squared here. Be careful when you're squaring this. So you're going to square the top, square the root 3, you're getting 3. Square the x, you're getting x squared. Square the bottom, you're getting 4. And you're getting exactly the same here. Minus 2 times, so have a look at these. This is, that x should probably be inside the brackets, doesn't make a difference. But those two there, that's just like taking root 3 over 2x and squaring it. So we get exactly as we did, 3x squared over 4 times the cos of the angle A. So what's left to do is just to simplify, we're going to put these two together. So x squared stays as it is on the left. Now have a look at what you have here. You have 3/4 of something, an x squared, plus another 3/4 of the same thing, x squared. So when you add 3/4 and 3/4, you get 3 over 2 x squared. Over here, we have minus 2 times 3x squared. That gives me minus 6x squared. And minus 6x squared divided by 4 is minus 3 over 2 x squared. Times, remember, your cos A. And remember, what we don't do for definite is we don't put all of this together, because this term here has a cos A hanging on the end. What we do is we basically subtract. So we're going to subtract that from both sides. So that will give me x squared minus 3 over 2x squared equals minus 3 over 2x squared times the cos of the angle A. Left-hand side, that's going to give you minus a half x squared equals minus 3 over 2x squared times the cos of A. And then this guy here is in the way of getting that cos A on its own. So what we're going to do to get rid of it is we're going to divide both sides by minus 3 over 2x squared. So when you do that, you'll notice this will cancel out. You'll also notice that this x squared and this x squared will cancel out. And if you throw minus a half divided by minus 3 over 2 into the calculator, what you should end up with is cos A is equal to, your halves cancel out, so cos A is equal to 1/3. Okay, so if we just run back here to the question asked us to find the cos or the cosine of the acute angle, and that's exactly what we've done. We could go further and find the angle, but we've not been asked that in the question. Okay, so as you can see, a little bit of a slog, loads of work, and we started basically by using Pythagoras' theorem twice and then into the cosine rule. So the maths part of it, I suppose, is very straightforward, but it's knowing where to start in the question is the hard part with that one, especially when you're not given any numbers. Okay, so sticking with 2019, we're going to move on to a longer question from that year. And this was looking at a helicopter pad. So this is 2019, it's paper 2, and this one was question 9. So first of all, we're looking at a diagram, shows a triangular patch of ground with SH equals 58, so that's marked in, GH is 30, and the angle GHS is 68, as is marked in. And it's important to note here that the circle is the in circle of triangle SGH. So we're going to need that information at the very end of the question. So the first thing it asks us is to find the distance from S to G, give our answer in meters. So make sure to put our units in our answer, and we're rounding to 1 decimal place. So SG is this side over here. First of all, it's not a right angle triangle, so Pythagoras is no good to us, nor are sine, cos and tan. We don't know a side, opposite angle and another piece of information, so we have to use the cosine rule here. So straight in with my formula, times the cos of angle A. And remember, you always start with the side that's opposite the angle that you're looking for or the angle that you're given. So in this case, the angle I'm given is 68. So the side I'm looking for has to be this one here. My A has to be this one here. So that's going to give me SG, the distance from SG squared, is equal to 30 squared plus 58 squared minus 2 times 30 times 58 times the cos of 68 degrees. And because there's no variables on the right hand side here, that can go straight into your calculator. Just make sure that your calculator is in degrees, not radians. So what that should give you is 2960.369. And don't forget, that's SG squared. So to get SG, we basically find the square root of both sides. So we square root here, we square root here. That knocks off the squared on the left, and it will give you 54.4 meters, and that's correct to 1 decimal place as we were asked. So what I'm going to do, good habit to get into, as I said already, go back to your diagram and fill in your answer, because you will probably need it at some stage later. Part B, find the angle HSG. Okay, so we note where that is on the diagram. We look at the middle letter, remember, and that's that angle there. So I'm going to call it X for now. Give your answer again in degrees, correct to 2 decimal places this time. So this time we're actually fine to use sine rule, because now we do have an angle side opposite it and another piece of information. So that's going to be A over the sine of angle A equals B over the sine of angle B equals C over the sine of angle C. Now, when we're using the sine rule, we only ever really use any 2 of those, so we're just going to pick the first 2. So A is any side, and capital A is the sine of the angle across from it. So we're going to start with, because we have 54, as I said, and the angle opposite is 68, we're going to start with those. So it's going to be 54 over the sine of 68 degrees. Sorry, that was 54.4, wasn't it? Yeah, over the sine of 68 degrees is going to be equal to 30 over the sine of, we've just called it angle X. So back to your diagram, as you can see, 30 is directly across from angle X. So that's why I'm using that. So what we have one fraction equals to another. So we're going to cross multiply here, and that gets rid of fractions for us. So we're left with 54.4 times the sine of angle X equals 30 times the sine of 68 degrees. Okay, so this part can go straight into our calculator. That gives me 54.4 times the sine of angle X is equal to 27.8155. We're going to divide across by 54.4. So that will give me sine X on the left is equal to 27.8155. And we're dividing both sides by 54.4. And finally, sine is in the way of getting that X on its own. So when we get the opposite of sine, it becomes sine inverse. So sine inverse of what we had at the right hand side. And it's just a matter of putting that straight into your calculator. So your angle HSG, as they called it, is equal to 30.75 degrees, and that's to 2 decimal places. So again, get in the habit, go back up here and mark in your angle just in case you lose where you are later. and you will need that angle. Okay, moving across here so that I can still kind of see my diagram. We're asked to find the area of the angle of the triangle SGH and give our answer in meters squared, correct to 2 decimal places. So what we're going to use here, we're going to use our trigonometry area of a triangle formula. So that's a half AB times the sine of the angle C. So that's going to be half the product of any two sides. Doesn't matter which two sides you pick. I'm going to pick 30 and 58 times the sine of the angle in between. So that's the sine of 68 degrees. And that's going straight into your calculator. It should be giving you 806.65 meters squared to 2 decimal places. Okay. Next part D, part 1. Find the area of the triangle HSP. So let's see where HSP is. Just going to mark that in on my diagram. There's my triangle HSP. And this time we're giving it in terms of R, where R is the radius of the helicopter pad. So up here in part C, we use our trigonometry area of a triangle formula. But we also had another area of a triangle formula. That was half the base times the perpendicular height. And I'm going to use that straight away here because you'll notice from your diagram, this angle here is a 90-degree angle because the radius going to the tangent, so there's my tangent, a line touching a circle at one point only, is always perpendicular. It's always 90 degrees. So what I can use for my half my base, when my base is going to be 58, as we've marked there, and my perpendicular height is going to be R. So putting that into your calculator, half of 58 is 29, 29R, and again our units are meters squared in this case. Okay, so that's using both of our area of our triangle formulae. Part B, part D, part 2. Show that the area of the triangle SGH in terms of R can be written as 71.2 R. So if we go back, we're going to need to find the area of SGH, triangle SGH in terms of R. So what I'm going to do is I'm actually going to split it up into 3 triangles. I'm going to draw another line from G to P there, and I'm going to split this triangle up into 1. So this triangle here, 2, so this triangle here, and 3, so this triangle over here. 3 different areas. So my area 1, we've just worked out, is 29R. My area 2, so that's the top triangle up here. If you like, let's just put in another radius here. So that's also going to be R, and let's just put in another radius here, because the radius of the circle is going to be the same, no matter what point on the circle you go to. So for area 2, it's going to be half the base by the height. So again, this time it's half of 54.4 times my radius, and my area 3 is going to be half of 30 times my radius. So in each case, the radius is perpendicular to the line, the tangent. So putting all of these together, we're summing them all together, remember, we should be getting 71.2 R, and your units are going to be meters squared. Okay, so that's using our half the base by the height formula. And over to part 3, find the value of R, give your answer in meters correct to 1 decimal place. So let's just remind ourselves what we did here. Up here, what we did in part C was we found the area of the triangle SGH and we got 806.65 meters squared. Down here, we found the area of SGH in terms of R, and we said it was 71.2 R meters squared. But remember, in either case, you're talking about the same triangle. So you're still talking about the area of triangle SGH. So that's going to be 71.2 times R, that's coming from here, remember, is going to be equal to 806.65, that's coming from over here. So the 2 must be equal because it's exactly the same triangle, and all we're doing is we're dividing across by 71.2. So what that should give you is it should give you a radius of that circle of 11.3 meters. Okay, and the last part we're going to have time to get done today is part E. So this is a 3D problem. ST is a vertical pole at the point S. The angle of elevation of the top of the pole from the point P is 14 degrees. So that means if I was standing at P and I was looking up to the point T, that angle right there would be 14 degrees. Find the height of the pole. So it's TS over here that we're looking for. Let's just mark in some things we might use. This length here, H to S, was 58, remember? And this here was our radius, which we've just worked out is 11.3 meters. Okay, so what we're going to do, we're actually going to start with that triangle HP and S. So let's draw that down here. And it's a good idea to draw that sometimes for yourself, just so you can see clearer, a little bit clearer what's going on. So that line there is 11.3. Our angle is 90 degrees, and this full length here is 58 meters. Okay, and what we do know is we know that this angle here is going to be half of 30.75 degrees. So that's 15.375 degrees. Now, where have I gotten that from? Well, that angle there is half of the angle GSH. And if we just go back here for a second, we have worked out the angle GSH. Where did we do it? We did it back here in part B. So we worked out the angle GSH or HSG back here as 30.75. But remember, we were told up here that the center of the circle in the center was the in circle. And we know that the in circle and the in center come from bisecting angles. So to bisect an angle means we're cutting it in half. So that angle GSH is cut in half, and that's where I'm getting 15.375. Okay, so that angle there, 15.375. So taking my right angle triangle then, I am going to try figure out the distance from S to P. So this is my question mark. 11.3 is my opposite. S to P is my hypotenuse. So I'm going to use sine. Sine of 15.375 is going to be my opposite, which is PS. Sorry, opposite is 11.3 over my hypotenuse, which is PS. And solving that equation, that should tell you that your distance from P to S is 42.6197. So that's that line there, 42.6197. And finally, we're going to move on to that right angle triangle, P, S, and T. What we do know is that's 14 degrees. What we've just worked out is that that's 42.6197. What we're looking for is this side. So because we are looking for the opposite, we have the adjacent. This time we're using tan. Tan of 14 is going to be TS over 42.6197. And to solve that, you should end up getting that the distance from T to S, the height of the pole, to one decimal place, which is exactly as we were asked up here, you should be getting 10.6 meters. Okay, so I've gone slightly over time there. I apologise about that. Hopefully we found that of some use, so quite a bit packed in there. And of course you have your 2 videos in the chat also. Thank you.